Let's dive into this explainer and program our brains to conquer physics math problems with the flawless efficiency of a robot engineer. If you have ever stared at a Cambridge physics past paper question, especially those tricky ones from syllabus codes like 0625, 0651, 0652, 5054, or even the advanced 9702, and felt your mental circuits completely overload, I want you to know that you are definitely not alone. It is a universal experience. But today, we are going completely rewrite your approach. We are going to treat your exam strategy exactly like a software program, feeding it the perfect code so that you can automate your success and entirely eliminate those frustrating mark-costing calculation errors. Let me paint a picture for you. We typically see two types of students struggling. First, there's Alex. Alex tries to memorize the entire textbook, overloading answers with raw physics acts but providing zero analytical logic. Then there's Sam. Sam rushes through, completely misses the specific command word requirements, and drops crucial steps. Both of these approaches lead to massive point deductions, leaving the examiner's red pen all over the page. Today, we transform you from an Alex or a Sam into a flawless calculating machine.
To achieve this massive transformation, we are going to install 4 crucial system update modules today. First up, we'll establish the physics math algorithm, the baseline code for your success. Second, we will master rearranging the code so you never get stuck on a tricky variable. Third, we're going to tackle complex calculations and BIDMAS, debugging the most common errors students make. And fourth, we'll finish up by factoring in direction, ensuring your vectors are always perfectly aligned.
All right, let's boot up our foundational subroutine, the basic physics math algorithm. This is the absolute core logic you need to apply before your fingers even touch the buttons on your calculator. For written theory questions, top students rely on the Peel framework, point, evidence, explanation, link, to structure their thoughts. But when it comes to raw calculations and math-based command words in a Cambridge physics exam, your equivalent of Peel is a strict, step-by-step mathematical algorithm. You cannot just guess and check. You have to lay down the code logically so the examiner can see exactly how your brain is processing the raw data. At the heart of this algorithm is the equation. An equation is simply a mathematical description of a relationship between real, physical quantities in our universe. It allows us to calculate an unknown value instead of trying to go out and measure it physically. Think about how powerful that is. Instead of trying to construct a giant scale to physically weigh an incredibly massive object, if we just know its mass and the gravitational field strength, we use an equation to instantly find the weight. It is a massive shortcut, provided we understand how to read the relationship properly. Now, before we continue and dive into the exact rules of manipulating these equations, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, I need you to pay close attention to this system warning. Maintaining equality across the equal sign is the absolute golden rule of our mathematical algorithm. This is where a student like Sam usually crashes and burns. The equal sign literally means the same as. It is a perfectly balanced scale. If you have a simple, universally true equation like 3 + 4 = 7, and you decide to add 2 to the left side, you absolutely must add 2 to the right side to keep it true. Whatever mathematical operation you perform on one side of your code, you must mirror on the exact opposite side. If you square the left, you square the right. If you divide the left by time, you divide the right by time. And this brings us to the ultimate 5-step master algorithm. This is your physics success blueprint. If you execute this loop for every single calculation you encounter, you will drastically maximize your mark potential. Step 1. List out the exact variables the question gives you. Write them down clearly. Step 2. Scan for and convert any inconsistent units. If the mass is given in grams but your formula requires kilograms, you must fix it right now before moving forward. Step 3. Choose the correct equation that leaves only one single unknown value. Step 4. Substitute your known numbers into the code. And finally, step 5, calculate your unknown value and never ever forget to write down the final unit. This is how you change those red examiner marks into bright green check marks. When you structure your answer using these 5 steps, even if you make a tiny calculator error at the very end, the examiner can still award you almost all the method marks because your logic is visible and flawless. Moving smoothly on to Module 2, we need to learn how to manipulate our software by rearranging equations safely. Sometimes the exact value you need isn't sitting nicely at the end of the equation. You have to go in and dig it out without breaking the rest of the code. When your required unknown value is buried deeply inside a standard formula, you must rearrange it to make it the clear, undeniable subject on the left-hand side. We call this changing the subject of the equation. We prefer our target variable on the left because, quite simply, human beings read equations from left to right. Getting your unknown variable completely isolated on that left side makes the final calculation incredibly straightforward and prevents those silly avoidable errors under exam pressure. Let's break down the exact mathematical steps to isolate variables using simple multiplication and division rules. We achieve this by choosing a specific value to multiply or divide by, purposefully forcing terms to cancel out. For example, if you know the classic equation weight equals mass times gravity, but your command word asks you to find the mass, what do? You simply divide both sides by gravity. The gravity terms on the right side cancel each other out perfectly, leaving mass beautifully isolated. Then you just flip it around so mass is on the left. It's elegant, it's logical, and it is entirely foolproof when you apply that golden rule of equality we just talked about. Or consider finding pressure. If pressure equals force divided by area and you need to find the pressure, well, that one is already perfectly arranged for you. The key is recognizing when you need to act and when the formula is already giving you exactly what you need. Understanding these variable relationships allows you to act like a supercomputer, predicting if your final output should scale up or scale down before you even hit equals on your calculator. This is an incredible tool for double-checking your work on the fly. Think back to that pressure equation. Pressure equals force divided by area. If the area, which is the number sitting on the bottom of the division fraction, gets much smaller, the final answer for pressure gets massively bigger. They are inversely proportional. This is exactly why stepping on a tiny, sharp stiletto heel exerts way more pressure on a floorboard than a wide, flat sneaker, even if the person's total weight is exactly the same. If your calculation says the stiletto exerts less pressure, your predictive brain should immediately flag that as an error. Let's boot up Module 3 and see how all of this builds into solving complex, multi-step calculations. In those high-mark, higher-tier Cambridge physics problems, plugging numbers into a single equation is rarely going to be enough to get you to the finish line. A lot of these advanced problems require chaining more than one equation together. Notice how a common foundational variable like energy links multiple formulas like kinetic energy and thermal energy all together in a web. You might need to use the equation for gravitational potential energy to find the total energy gained by lifting a heavy steel block. And then you have to take that exact energy value and plug it directly into the power equation to figure out exactly how powerful the crane doing the lifting actually was. Energy acts as this amazing universal translator between totally different sections of the physics syllabus. Now stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade bounders. Join them right now by subscribing to @the_ACEexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Welcome to our interactive workshop. I want you to imagine a complex data table in front of you. Just like reading sentences in a book, equations are naturally read left to right, but the actual calculation order inside your calculator must strictly follow the BIDMAS protocol. Brackets, indices, division and multiplication, then addition and subtraction. If you just type a long, complex string of numbers into your calculator from left to right without thinking about resolving the brackets and indices first, your calculator is just going to blindly follow its basic programming and give you the completely wrong output. You have to be the pilot. You have to tell the machine what to process first. Let's do a quick challenge. Find the flaw in your own thinking. Do you calculate the multiplication first just because it comes first in the sentence? No, you follow BIDMAS. Let's look at a concrete example of applying this. When calculating gravitational potential energy, your algorithmic first step absolutely must be to calculate the change in height within the brackets before you do any multiplying. If a heavy elevator travels from 4 meters above the ground up to 18 meters above the ground, you must perform that subtraction inside the brackets first to get an exact 14 meters of height change. Only after you have that single value do you multiply it by the mass of the elevator and the gravitational field strength. Processing the brackets first ensures your code runs perfectly, and your final energy value is spot on. Here is another incredibly critical system warning that catches so many students off guard. Premature rounding in your intermediate code steps will permanently corrupt your final answer. When you are working through these multi-step chain calculations, keep those long, messy decimal numbers stored safely in your calculator's memory. Do not chop them off. If you round off too early, say to 2 decimal places in step 1, those tiny little inaccuracies will multiply and amplify throughout the rest of your equations, leading to a final output that is just far enough off to lose you the accuracy mark. Always, always wait until the very last step to round to the appropriate significant figures. Finally, let's load our last and perhaps most vital module for the higher tier papers, calculating scenarios that involve physical direction. In the physical world, it is not just about how much raw force you apply to an object, but exactly where you aim it. In physics calculations, direction dramatically alters the final physical outcome, which is exactly why we must program our brains to instantly recognize vectors. A vector is a variable with both a magnitude, meaning its size, and a specific direction. Think of 2 bumper cars at a carnival. If they are moving fast in the exact same direction and one gently taps the other, it's barely a bump. But if they are moving with that exact same speed in opposite directions, head-on, it is a massive, jarring crash. The mathematical code has to account for that directional data, particularly when we are dealing with momentum, velocity, or, as we are about to see in our final challenge, turning forces. When you are dealing with turning forces, which in physics we call moments, visualizing the central pivot point and mapping out the directional forces is an essential processing step. Just like the children placed on a seesaw, a moment is simply a force multiplied by its perpendicular distance from the pivot. But crucially, a moment isn't just a raw number, it is a tendency to turn the entire system either clockwise or anti-clockwise. If you are calculating exactly where a third child needs to sit in order to perfectly balance the seesaw, your very first step has to be sorting the forces by their turning direction. You literally have to categorize them into team clockwise and team anti-clockwise. So the absolute crucial takeaway here is that for any physical object in a state of equilibrium, meaning it is perfectly balanced and not turning, your total sum of anti-clockwise moments must mathematically equal your total sum of clockwise moments. This is the famous principle of moments. By setting up a balanced equation where all the anti-clockwise turning effects are placed on the left side of the equal sign and all the clockwise turning effects are grouped on the right side, you create a perfectly stable mathematical model. From there, you simply run your rearrangement subroutine that we learned earlier to easily find the missing distance or the unknown force. You have the complete physics answering system now. 3 rules guarantee top marks: command word decoding, framework application, and strict time management. Students who implement these physics strategies see an average improvement of 2 whole grade boundaries. But that only happens if you practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the absolute biggest challenge you're currently facing. Our expert team responds to every single comment. Like and share this video with a study partner right now so you can hold each other accountable. Keep practicing, trust your new algorithm, and remember, ace the exams. Your Cambridge success starts here. I'll see you in the next session.